friends. Happy Wednesday. Happy December. I hope the summative went well yesterday. Today we're going to introduce how to do some math with free fall, so word problems. So you want your packet out. We're going to go through this video. Please pause it at any time. Rewatch it if parts are confusing. I know this is not an ideal way to learn. I appreciate your flexibility, your willingness to be persistent, to watch the video, to stick with it. And yeah, just email me any questions, but we've got to get through this, okay? All right, so remember all these equations you've learned throughout the semester. Some Mr. G taught you, some I taught you. We're going to use these same equations with free fall. So there's no new equations. We're going to use the same ones, and we're going to solve problems in free fall. The one thing I want to point out is this first one. You can always ignore this in free fall because that equation, if I go back, is when the velocity of an object is constant. So that would be like a car moving at a constant velocity or a person running at a constant speed. When things are in free fall, they're accelerating because there's a net force acting on them. The force of gravity is the only force. So there's a net force, and so they have acceleration. So this equation we will not use during this unit. The rest of them, we're going to use all of them. So we've got 2 from Unit 1, 2 from Unit 2, and 3 from Unit 3. All right, so you're going to go to page 30 of your packet, and I'm going to work you through pages 30, 31, 32 together. So the setup for this activity, we would do this if we were in class, is that you're dropping a heavy object and a light object. So I enlisted the help of my 3-year-old, and I have a video of him dropping a piece of petrified wood, which is a super heavy old rock, and a block with letters on it. So it's a pretty light piece of wood. So 2 very different massed objects, and let's take a look at what happens.
I have a block and...
I gotta make sure this sound is working on this.
What? What did I see when I turned it all the way over?
What is it?
This goes in my name!
You have an E in your name?
Yeah, I knew, and wait, these both are in my name. R and E.
Yes, that's exciting. So what's in your other hand?
Rock.
A rock. Okay. Which one do you think is going to hit the ground first?
This one.
All right. We're going to try. You got to drop them at the same time from the same height, and don't throw them, just drop them, okay?
Okay.
Ready?
All right, so I'm not going to, sorry about that. I'm not going to tell you the answer quite yet. We're going to predict it using physics. I know, what a cliffhanger. Oops. So, all right. What's your prediction? I want you guys to predict. What do you think is going to hit the ground first? Cooper thinks the light one's going to hit the ground first. Some people think the heavy one. Some people think both. So make a prediction in your head, and then let's do these calculations. All right, so step 1, the first thing we're going to do is an energy calculation to find the final velocity. How fast are those objects going when they hit the ground? So to do that, we're going to do an LOL diagram, just like we did in energy. So starting initially is when Cooper's holding it at rest. Final is the moment before it hits the ground. So for the small object, it's going to start with a small amount of UG. So UG is mass times gravity times height. It has a small mass, so I'm going to give it a small amount of UG. We're going to ignore air resistance, so no work. And then it ends with a small amount of K. Those should be equal. I didn't make my boxes very well. Okay. So my energy equation is UG plus 0 is equal to K. All the potential energy when Cooper's holding it at rest is all getting transformed into kinetic energy. So my equation would be mgh equals 1/2 mv squared. We need some variables here. We need some actual numbers. This is SEP 5A. We're doing calculations. So what are these, Mrs. Rona? Let me tell you. Wonderful. The mass of the small object, so the little block, is a 10-gram block, so 0.01 kilograms. The height, I looked up Cooper's arm height. It's 0.76 meters, so if he just puts his arms out and drops it. And gravity on Earth is 9.8 newtons per kilogram. So then we're trying to solve for final velocity. So I want you to pause the video here. Use this equation to solve for the final velocity before it hits the ground. So pause it, try it, and then I'm going to talk you through it. All right, so I've got the mass, gravity, and height, the mass and velocity squared. So if you multiply the left side together, you get this number. You multiply the right side, you get this number, and then we divide by that 0.005. That gets me v squared. Then I have to take the square root of both sides, and you should get 3.86 meters per second. So that's the velocity we would expect the small block to have when dropped from this height right before it hits the ground. If you need to rewind or go through that again, pause, whatever, do that. Let's do the same thing for the heavy block. So the heavy block down below, it starts with lots of UG because it has more mass. So ends with more K. So our UG is equal to 0 or plus 0 equals K. MGH equals 1/2 MV squared. So that's my equation again. Same scenario, different variables. So now the mass of that heavy object, it's about 1 kilogram. It's a heavy rock, okay? It's about 2.2 pounds. So 1 kilogram times the gravity times the height. Pause the video again. Solve for the final velocity. How fast is the big thing going before it hits the ground? All right. Hopefully you did that. This is where you've got to have some discipline, right? I'm not there. I can't make you do it. Hopefully you paused and calculated. And you found, wait a minute, Mrs. Rona, I got the exact same number. Did I mess up? You did not mess up, okay? So these are the numbers you should get. You take the square root, you get 3.86 meters per second again. Hold up. Flip over the page, page 31. Something happened. They have the same velocity. So let's say the mass was double the mass. Why should it make sense that you have the same final velocity using proportional reasoning? So this is a preview for tomorrow, but we could prove that they should have the same using proportional reasoning. So same equation, MGH equals 1/2 MV squared. If it has twice the mass, I'm going to plug in a 2. Gravity stays the same, so I plug in a 1. Height stays the same, so I plug in a 1. The 1/2's a constant, so I plug in the 1. The mass doubles times v squared. Well, if I have a 2 on this side and a 2 on this side, I divide by 2. I get that the velocity is 1 times as big. It stays the same. So no, the mass does not affect the final velocity. They're both going to hit the ground going the same speed. But that's not what we tested with Cooper. We tested how much time, which one was going to hit the ground the soonest first, right? Which one takes more or less time to hit the ground. So this is important, energy, but we need to get to time. So what else do I need to know is I need to know something with forces. All right, onward on page 31. So we're going to use forces to find the final acceleration. Not the final, that should just say acceleration. To find the acceleration of the object while it's falling. So starting with the free body diagram, for the small object, it's going to have a small weight. Weight is the same thing as Fg, so this is a small arrow down. Nothing in the x direction. In the y direction, my F net y equation is negative Fg to mark downward, and then I set it equal to ma because F net equals ma. So this is my setup because my force is going down. I've got negative Fg, and I set my F net equal to ma. The velocity is down, the net force is down because the only force is down. And since net force causes acceleration, acceleration's also down. So now I want to calculate the acceleration. So I'm going to use this equation right here. Negative Fg equals ma. You want to make sure you write your equation before you plug in any numbers. So how do I find Fg? Well, we have an equation for that. So over to the side, let's do our calculation. Fg is mg. We always know we can calculate Fg by doing mass times 9.8. So I'm going to take the small mass, which was 0.01 kilograms, times 9.8, and find the weight of it, which is, that should be an equal sign, not a minus. Fg is 0.098 newtons. That's the weight of the little block. Now I can plug that back into this equation here for Fg. So I have negative that, because my Fg is downward, is equal to 0.01 A. That's the mass of the block. Divide the mass to the other side, and I get A is negative 9.8 meters per second squared. That's the acceleration of the small block when it was falling. I found that by finding the weight of the small block and setting it equal to ma because F net equals ma. All right, pause the video, try this for the big block, and then I'm going to go through it. All right, big block, a bigger weight. Okay, still only one force going down, but it should have a bigger arrow because it has more weight. Still nothing in the x direction, same F net y equation. Velocity, acceleration, and net force are down. Same calculation, but now we plug in 1 kilogram for the mass. That was on the page before, right? On page 30, we used 1 kilogram for the big object. So this is 9.8 newtons. We plug that in and we get, wait a minute, the same acceleration. Both objects have the exact same acceleration, even though they have different masses. They both accelerate at negative 9.8 meters per second squared. Whoa, bottom of page 31. How do they compare? They have the same. And here's the reasoning. Here's why it makes sense using forces. Even though the big object has more Fg pulling down on it, it also has more mass, making it harder to accelerate. So since it has a bigger Fg and a bigger m, those two cancel each other out, so we get the same acceleration. That's a big idea. We're going to write that on the top of page 32. All objects in free fall on Earth accelerate at negative 9.8 meters per second squared. Now, this is in the absence of air resistance. So if you have a parachute or a whole bunch of wind pushing up on you, you do not accelerate at negative 9.8 meters per second squared. But if I drop a pencil, a pen, myself, a rock, a block, every object in free fall on Earth accelerates at negative 9.8 meters per second squared. That's going to be a big idea that we use for all problem solving in this one, that we're going to plug in negative 9.8 for the acceleration of objects in free fall. All right, one more step. The question with Cooper was not which one was going fastest or which one had more acceleration. It was time. Which one had more time? So let's go on to part 3 to use kinematics to find the time it's going to take to hit the ground. So kinematics are these 3 equations from Unit 1, and we want to solve for the time. So my animations appear to be off, which is fine. So it's calculate the time for the small object and the big object. Well, here's the object, right? It starts at a height of 0.76. So going back to Unit 1, x0 is the initial position. X is the final position, so it ends at 0 meters. Those are our labeling on our diagram. It started from rest. Remember I told Cooper, don't throw it up, don't throw it down, just drop it. So it's 0 meters per second. And this big idea we just learned, the acceleration of things in free fall, once they leave your hand, they accelerate at negative 9.8 meters per second squared. What am I solving for? I'm solving for time. So now once I've listed out these variables, I need to pick an equation. Is it the first, second, or third equation? Well, hopefully you know it's not the first, right? We started off today by saying don't use this equation. The second and third equation both have time in them, right? A time here, time here. So I've got to decide which one I have other information for. Well, I know initial velocity, that's in both. I know initial position, that's in this one. I know acceleration, that's in both. And I know final position, that's in this one. So since I know all the variables in this one, I'm going to use this equation. The other way to think about it is in this equation, I don't know the final velocity. I don't know how fast it's going before it hits the ground. Not when it hits the ground, right? But the moment before it hits the ground. Actually, that's a lie. We know it from energy, don't we? Okay, you could use both equations, I just realized. I'm going to show you how to use this equation. The way you would use this one is we, in step 1, found the final velocity. I think it was 3.86 meters per second. So you could use this one if you'd prefer. But I'm going to show you this one. All right, so first step is you write your equation in variable form. If you don't write it like that, you can't get a 3 on your formative or summative. Then you plug in your numbers, just whatever you have on your diagram. So x is 0. Acceleration in free fall is negative 9.8. That's for all objects always in free fall forever and ever on Earth. T is what we're looking for. Initial velocity is 0. T is also what we're looking for. And initial position is 0.76. Now the nice thing here is 0t, this cancels out, which is good. Otherwise it would be a quadratic and we don't want to deal with that. So this cancels out. So I would subtract the 0.76 to the other side, and I get negative 0.76 equals, I would multiply 1/2 times negative 9.8, negative 4.9 t squared, divide by negative 4.9, and then take the square root of both sides. So I get 0.39 seconds. That's how much time it takes the small object to hit the ground. My work went down here, because guess what? That's how much time it takes the big object to hit the ground as well. Why? By what factor is it different? Justifying the equation. Well, looking at this equation, everything in this equation stays the same. There's no mass in there. And so